Hi folks, welcome to Unit 5, Lesson 8, the last lesson of this unit. So what we're going to go over is some rules about exponents. So we're going to take a little detour from what we've been working on. And the first thing I'm going to have you do is work through number 1. This is essentially just a review of the exponent rules that you would have learned over the last couple of years. So go through the process, make sure you're remembering these particular properties, and we'll come back and take a look at them together. So take maybe 6-7 minutes to go through all of number 1, and then we'll be back. So please turn off the video now, and we'll see you in a little bit. Okay, so we're back. So let's take a look here at things that hopefully looked very familiar. It says consider the product of two powers with the same base. And while this is not a proof, it just demonstrates what the property is. So if I've got x to the 5th times x cubed, and I write them both as this series of multiplications of the same number by itself, and because the order in which we do multiplications doesn't matter, so I don't have to multiply all of these together and then multiply it to the product of these three. I can mix and match. So this is the same as multiplying all these 8x's with each other. So in other words, this is equal to x to the 8. And hopefully remember that that's what leads us to the rule, that as long as the two powers have the same base, the result is just going to be another power with the same base, where we just add the exponents. All right. So very important that this only works if they're the same base, because if this was y times y times y, there would be no way to combine them. I would just have to keep the x's and y's separately. So here our rule, which of course is called the first exponent law, is that if I have the product of two powers with the same base, I get a new power with the same base and the exponents added together. All right, so hopefully you saw that the next one was pretty similar. So here we have the quotient of two powers of the same base. So I have x to the 5th over x cubed. All right, and what we can do is we can reduce any common factors that exist in the numerator and denominator. All right, so just to justify why this is the case, because I can rewrite this fraction as x over x times x times x times x times x all over x times x. This is equivalent to each other, because how do we multiply fractions? We multiply the numerators, so that would give me the same numerator, and we multiply the denominators, which would give me the same denominator. But once I've got this expression here, x over x is just equal to 1. So we can reduce two common factors in the numerator and denominator. So I can reduce those x's, and I can reduce these x's, and I can reduce those x's, and all I'm left with is 1 in the denominator, and in the numerator I'm just left with 1 times x, which is x squared, which leads us to our rule for the quotient of two powers with the same base, is we notice that we just subtract the exponents. All right, not a bad idea though sometimes to remember why this actually works. All right, so here when I divide two powers with the same base, I get another power with that same base, but I am now subtracting the numerator power, or numerator exponent, by the denominator exponent. That's the second exponent law. All right, and similarly when we have the power of a power. So if I have x to the 5th and all of that cubed, well, that's like taking x to the 5th times x to the 5th times x to the 5th. But again, I can multiply these all at once, since the order doesn't matter. And in the end, we count, and we've got 15 of those x's that are being multiplied, and that's where we reach the third exponent law, which if I have the power of a power, that gives me a power with the same base, but with the exponents multiplied. All right. So another thing that's pretty useful is this idea of taking the power of a product. Okay, so here I'm looking at 6 cubed. Okay, so what is 6 cubed? Let me, not coming to me right off the bat. So 6 exponent 3 is 216. Should have been able to do that in my head, but I guess it's late. So we have 216. Okay, and here we have 2 cubed, which is 8 times 3 cubed, which is 27. And well, what happens when we do 8 times 27? Lo and behold, we get 216. Now you might say, well, what's the point here? Well, here 6 can be written as 2 times 3. Okay, so whether I first multiply the 2 times 3 and then cube it, or cube those numbers individually, it doesn't make a difference. I get to the same value. Now, of course, you have to be careful because this does not work when we're adding two numbers in the bracket. And if you test it out, well, 2 plus 3 is 5. Okay, so 5 squared is 25. But if I do 2 squared plus 3 squared, I do not get 25. Okay, I get 9 plus 4 is 13. So this here works for products, but not sums or differences. So how can we write a rule? A times b all to the n is the same as calculating a to the n times b to the n. So in other words, we can distribute the exponent to each of the factors inside the bracket. They have to be factors. Okay? But as we often see, when something works for multiplication, it often doesn't work for addition or subtraction, but there usually is a similar rule for division. And so let's see what happens. Well, if I have 3 cubed, and again, what I'm going to see is 3 is 6 divided by 2 cubed. Okay, and 3 cubed is 27. Okay, but when I now try to distribute this exponent to numerator and denominator like they did here, well, we know that 6 cubed is 216 over 2 cubed is 8. All right, and we saw from before, what's 216 divided by 8? Well, that's just 27, exactly what we got before. So this idea of distributing an exponent works also for a division. So a over b all to the n is the same as a to the n over b to the n. All right, and these would have been the basic rules of exponents that you would have studied back in grade 9. Okay, so done a little review of them, but if you noticed, all the exponents we worked with and all the examples we were able to work with were with these positive integer exponents, where I can interpret an exponent as how many times I multiply a number by itself. But the reality is that you can consider exponents that are not positive integers. So in other words, you can't think of them as multiplying a number by itself a certain number of times. So if you have x to the negative 3, what does it mean to multiply something by itself negative 3 times? There's no sense. Or what about x to the 2.7? How do you multiply a number by itself 2.7 times? Okay, so this idea of an exponent being how many times you multiply a number by itself works great when we're talking about positive integer exponents, but falls apart when we try to look at more complex ones. So we're not going to go all the way in exploring these other exponents, but we will look at a few of them. And the first thing we're going to start with is negative exponents. Okay, so you're going to go through this little exercise here and see if you can figure out what a negative exponent means. Okay, how can we interpret that? So I'll just ask you to turn off the video and spend maybe, again, 6, 7, 8 minutes exploring these negative exponents and see what you come up with. All right, so please shut the video now. All right, so we're back. So let's see what process they take us through. So the first thing they ask us to do is they ask us to use arithmetic to reduce or simplify this expression. So, what do they mean? What we did before, we talked about being able to reduce common factors in numerator and denominator. So here I see that both numerator and denominator have a factor of 7 that I can reduce, and here another factor of 7 that I can reduce. So all I'm left with in the numerator is a 1, and in the denominator I'm left with 1 times 7. Now I'm going to do these sort of in pairs here, because if I look at this here, I have the exact same expression, except now I'm thinking of it in terms of exponents. This is 7 squared divided by 7 cubed. So if we use our exponent laws, which are those things that we established earlier, well, what does that give me? It gives me that 7 squared over 7 cubed. I'd have to subtract the exponents, but 2 minus 3 is negative 1. But remember, these two things were equal. So if these are equal, it means that 7 to the negative 1 must be equal to 1 over 7. Okay? So that's interesting. Let's see if something similar happens with the other ones. All right, so again, if we do this using arithmetic, we see common factor 5 with a common factor 5 reduces to 1. 5 divided by 5 reduces to 1. 5 divided by 5 again reduces to 1. And what we're left with is, well, just 1 in the numerator and 5 cubed in the denominator. Okay, so now I took this exact same expression, but now I considered it as powers of 5. So if I now have a quotient, I can again use the second exponent law and subtract the exponents. And what do I get? 3 minus 6 is negative 3. But remember, these two things were equal. So that means 5 to the negative 3 is equal to 1 over 5 cubed. Okay. So before we move on to the last one, let's notice a couple of things. A negative exponent does not make the number negative. But what it does seem to do is it seems to give us the reciprocal of the base. Okay? So this cube portion doesn't change. So remember we talked about the absolute value. The absolute value stays the same, but this 5 to the negative 3 becomes 1 over 5 to the 3. Very similar to what we had here. 1 over 7 was the same as 7 to the negative 1. So based on what we're seeing, it looks like a negative in the exponent has the effect of giving us the reciprocal of the base. All right, and let's test this one out here. Okay, we have a common factor of x and x. Oh, sorry, should be doing that here. X and x, x and x, x and x. And so what are we left with? 1 over x squared. And if I apply the quotient rule here, not the quotient rule, but the second exponent rule, these two things are equal, I get, not surprisingly, x to the negative 2. So these are equal, these two must be equal. So that means x to the negative 2 must be the same as 1 over x squared. All right, and so this gives us now a meaning for negative exponents. So if I wanted to write something a little more general, x to the negative m is the same as 1 over x to the m. All right, and in particular, this is probably the one that's used most often, is if I happen to have x to the negative 1, well, that's the same as 1 over x to the 1, but of course we don't bother writing that. Okay, so the effect of a negative exponent is that the negative portion of that exponent gives us the reciprocal of our base. All right, so, well, so far now we have positive integer exponents. We now have negative integer exponents. The only integer that's missing is the one right in between, 0. So that's what you're going to be studying in number 3, is what does the exponent 0 mean? Okay, so this one shouldn't take too long. So maybe 3-4 minutes to work on number 3. And then we'll come back and take a quick look at it. Okay, so please turn off the video. All right, we're back. So again, you see how we're interpreting the same expression, but in two different ways. Because here, if I do 25 divided by 25, well, a number divided by itself is just going to be equal to 1. Okay? Then 27 divided by 27, again, a number divided by itself is just going to be equal to 1. Okay? Oh, and I just realized, this looks like there's a little part missing here. We're going to add something. Maybe you notice that something a little odd here. So what I did is I wrote 25 over 25 as 5 squared over 5 squared. But look what happens when we now apply the exponent laws. 2 minus 2 is 0. So 5 to the 0. So since these two things were equal, that must mean that 5 to the 0 must be equal to 1. And I don't think you'll be too surprised that we're going to write this as 3 cubed over 3 cubed. Okay, which again, if we apply the exponent rules, or exponent laws, 3 minus 3, 0. So that means that 3 to the 0 must be the same as 1. Okay, and now we come to a very interesting result, that any number to the exponent of 0 is just going to be equal to 1. All right, so it doesn't matter what the base is, I'm always going to get 1. Now, it'd be nice to just leave it at that, but I'm hoping that maybe there's one value of x that you might be worried about. Okay, what if x itself is equal to 0? I can't go through this process because I can't put, 0 to the 4 over 0 to the 4 and then apply the exponent rule, because I can't have the 0 in the denominator. So what does that mean about 0 to the 0? Well, this is a much more complex conversation. Maybe we'll have a little bit of it at some point. But for now, we'll just tell you what we say. We say that this is an indeterminate form. It's not quite clear what 0 to the 0 is. Okay, so like I said, if we have time, we'll talk about it a little more. So for now, this rule works all the time as long as x is not equal to 0. All right, so now what we've done is we've found a way to identify what any integer exponent means. Positive integers, what we had before, and now we've determined what exponent 0 and a negative exponent means. Okay, so what we want to try to do now is we want to try to see if we can apply this to some of the types of problems that you would have solved in grade 9, except now we're going to add these other exponents. All right, so here you should probably be taking maybe 10 to 15 minutes to sort of go through these. Try to simplify them as much as possible. But I want you to look, anytime I put something that's bolded and italicized, it must be important. Okay, there's a rule we follow, a convention we follow, that we try never to express our final answers with negative exponents. We always want to express them using positive exponents. So for example, we wouldn't leave an answer of 2 to the negative 4. We would try to simplify it. Even when there's variables, I don't want to see these negative exponents. So you need to think about how you're going to simplify or keep simplifying these expressions so that they don't have any negative exponents left. All right, so stop the video. Again, like I said, take about maybe 15 minutes to try to go through these, and then we'll come back and look at them together. All right, please shut the video now. All right, we're back. So let's take a look here. And I would say this first one's pretty straightforward because this just follows the rule that we had before, that negative exponent, the negative portion just creates a reciprocal. So this is just going to be equal to 1 over 2 to the positive 4 exponent. Now, of course, we can, because this is a nice small number, 2 to the 4 is just 16. We can just write that as 1 over 16. Okay. If this was 1 over 2 to the 20, I would just leave it as 1 over 2 to the 20. Okay. Now, this is interesting because we have the negative exponent in the denominator. So let me just follow the rule as it states. Okay. So I have 1 over, and what does x to the negative 1 mean? Well, it means 1 over x. But look what I've got here is I'm dividing a fraction. And how does one divide a fraction? By multiplying the reciprocal. And the reciprocal of 1 over x is just x over 1. And so my final answer is just, well, 1 times x is x over 1. There you go. So what it seems to do is it seems to take this negative exponent in the denominator and brings it up into the numerator, but as a positive 1 exponent. Okay, well, we'll see if that still applies. Okay, we'll see if this is just a coincidence, but I think once we get to to D, maybe we'll see that that actually makes perfect sense. All right, so let's take a look at C here. And so I've got 3/4 to the minus 3. All right, so let's take a look here at what we can do. Well, what does the negative do to the exponent? Well, it just takes 1 over 3/4 to the cube. Okay, but what is 1 over 3/4 cubed? Well, it's 1 over, remember what we saw, we can distribute this exponent. So this is just going to be 3 cubed over 4 cubed. Okay, but again, what are we doing? We're dividing a fraction. So that's the same as multiplying the reciprocal. So that's like 1 times 4 cubed over 3 cubed. Okay, but wait a minute. We can rewrite 4 cubed over 3 cubed as 4 over 3 cubed. And I want you to look at the first and last terms. And we see that this idea of reciprocal really does follow. Because what is the effect of the negative is to just give me the reciprocal of the base. So this base of 3/4 now becomes a base 4/3. And I still have the exponent 3 there. All right. So now we're starting to see some of the ways in which we can work with these negative exponents, and we can just avoid doing all these steps because now we know that the effect of the negative is just to give us the reciprocal of the base of that power. All right, so another neat little trick. So here, if we think about what we saw before, that x to the negative 1, the x, the power just got brought up to the numerator. Well, this is my conjecture. Does that mean that this x to the negative 2 is going to go down into the denominator and become x squared? And this y to the negative 3 is going to just go up into the numerator and become u cubed? Well, that's a pretty good conjecture. Let's see if it works. Okay, so let's actually go through the process and see if that's what we get. Well, x to the negative 2 is 1 over x squared divided by y to the negative 3 is 1 over y cubed. And as before, what are we doing? We're dividing fractions, so that's the same as multiplying by the reciprocal of the denominator. So this is the same as 1 over x squared times y cubed over 1. And lo and behold, what do we end up with? We end up with y cubed over x squared. All right. So now in the future, we don't have to go through this whole process. We know that that's x to the negative 2 in the numerator is just going to become x squared in the denominator, and y to the negative 3 in the denominator is just going to become y cubed in the numerator. And once you've justified the pattern, you can use it. All right, so let's move on to this one here. So before I do anything, why don't I apply my exponent rules? Okay, because I can do x cubed divided by x to the 1, subtract the exponents. So that gives me x squared. Then I can do, well, y squared, y to the negative 2. Well, there are no y's, so that's not going to change. Y to the negative 2. And then I can do z cubed divided by z to the negative 3. So z to the, well, 3 minus negative 3 is the same as 3 plus 3, 6. And there you go. Except I don't want to see this negative exponent. But now I'm going to use what I found in the previous example, and I know that the effect is just to put this y into the denominator. So we're going to have x squared z to the 6th all over y to the positive 2. Okay, and this is the most simplified form. All right, let's take a look at this second last one here. And there's lots of ways we could proceed, but the first thing I'm going to do is I'm going to use what we found in part C and say, you know what? I know what the effect of this negative in the exponent is going to be. It's just going to give me the reciprocal of the base. So the first thing I'm going to do before I do anything else is I'm just going to flip that base and make it 3x to the 5th, y to the negative 1, all over 2x squared y to the negative 1. And this now is going to become to the exponent of 2. All right, so this already has simplified my expression. Now let's start doing some more simplifying here. Well, there's nothing to do with the 3 over 2. Okay, so the 3 will still be in the numerator. I have x to the 5th divided by x squared, so 5 minus 2 is 3, so x cubed. And here I have y to the minus 1 divided by y to the minus 1, so negative 1 minus negative 1 is negative 1 plus 1. Hey, it's 0. I end up y to the 0, which I know from what we saw previously is just going to be equal to 1. Now, by the way, it actually makes perfect sense that I should get 1, because this, whatever it is, just represents some number, and I'm dividing it by itself. And of course, a number divided by itself is always equal to 1. And don't forget, we still have the 2 in the denominator. And now we're squaring everything. So now what did we see about multiplications and divisions that have a power? I can just distribute it to everything. Now, big warning here is don't forget that you're also squaring the coefficients. That's what people often forget, is they worry so much about the exponent rules and they forget about the coefficients. I'm squaring everything in here. So this is 3 squared, 9. X cubed squared. Again, power of a power, we multiply the exponents. Okay. Well, y to the 0 is just equal to 1, so 1 squared doesn't still equal to 1. And then in the denominator, 2 squared is equal to 4. All right, and that's as simple as we can get it. And folks, you're almost guaranteed one of these things here. Some crazy thing, and people are going to start simplifying inside the bracket and try to use exponent rules and deal with all this ugly stuff, and they don't realize that, hey, wait a minute, this is just some base, whatever it is, to the exponent of 0. And what is anything to the exponent of 0? Just 1. And there you go. That's why not much room was left. Okay, so these are the basics that we need for this course here, and it's essentially to be able to work with any integer exponent, whether positive, negative, or 0. All right, and we saw the rules that apply, and we saw how we can actually apply them. Okay, there is this little bonus here. This is something you'll be looking at in grade 11, but you might want to go through it if you have time. And here we notice that we're trying to determine what is up with fractional exponents. What in the world does exponent 1/2 means? And if you go through the little exercise, see if you can figure it out, and maybe we'll talk about it when I get back. Okay, so if you still have some time, you can now work on the homework. That's it for this one.